this. So this is a as if, right? So this kind of thing is as if, fictitious, kind of not real, okay? Fictitious. Okay. So now if you look at this problem, so you try to maximize a average. Now this kind of average, right? So this kind of to the power alpha, to the power minus. So this is known as a geometric average, right? Not a sum divided by 2, but a product, right? So this kind of average is known as a geometric average. And then the component of this thing, this one is the surplus of the worker, and then this one is the surplus of the firm. Now, why is it called a surplus? So here, W is the benefit of work. Okay, so if the worker accepts the deal, the worker will get W. Okay, and then if the worker rejects the deal, the worker will get U. So U is the benefit of without work. Okay, keep unemployed. Okay, and the difference, this is what we call the workers' surplus. Okay, so you can imagine, given U, the higher the W, okay, so then the worker will try to negotiate, will ask for a higher wage. Okay, so this capital W will depends on the wage, right? So the higher the wage, the higher the W. And then in Nash bargaining, we will call this U and V the flat point. So when you negotiate, you can flat your the other party if you don't go for the deal. I have a better offer. Okay, so the better is your other offer or your outside option. The higher the wage you can negotiate, right? So this is very natural. Okay, so for example, if the unemployment benefit, so U will depend on the unemployment benefit, right? So U is the benefit that the worker will get if the worker remain unemployed. So one major component, one determinant of the value of capital U is the unemployment benefit. Right. So here the higher the unemployment benefit, the higher will be the outside option of the worker, and then the worker will be in a better position to negotiate for a higher wage, right? Okay. So and you will expect the higher the wage, then the harder, right? So other things being constant, the harder will the worker find a job, right? Okay, because the worker asked for a higher wage. So this thing is, so this result is similar to the macro one-side model, right? But the mechanism is not the same. Now in the macro one-side model, the higher the unemployment benefit, the worker will be more choosy in the sense that it will set a higher reservation wage. Okay, and then wait for a better offer. And here is the worker try to get a higher wage, try to negotiate for a higher wage. Similar, but not the same mechanism. Not quite the same, but the result is similar. The same idea applies to the firm, right? Because as I said, the two-sided model, you kind of treat the worker and the firm symmetrically, right? So the firm also has this value of accepting the deal, right? So we'll agree on the wage and then hire the worker, and then this is the value of the jobs, right? Value of the jobs. So in particular, it will depend on the productivity or the output, right? Okay, and what about there's no deal, right? So what about there's no deal? So this V is the firm's counterpart of U. Okay, so the benefit of the benefit of a vacancy, right? So keep a unfilled vacancy. Now you check back this Bellman equation, and then you see they are quite symmetrical. So in the notes, so we got all these things. Okay, so here, so this is the worker and the firm's value of work, right? So this for the workers' value of work, this is for the firm the value of a field job, right? The value of a job. And here, given a wage W, okay, so for any given wage W, so if the worker accepts the job, there will be a flow return of W every period, and then the continuation value depends on whether the worker can keep the job or not. So this delta is the job separation rate. So here in this model, job separation is exogenously given. So in every period, there's a chance the worker, the match pair will be dissolved. Okay, so so the delta is a probability. You can take this delta to be probability. Okay, so so there's a probability of delta. The worker will lose the job, and then he will go back to the unemployment state. Okay, so get the benefit of unemployment. You get the value, right? So now all these U, W, J, and V, they're all the present value, right? So the value function of in a given state. Okay, so W is in the state of employment, U is in the state of unemployment. Similarly, for the firm's counterpart is that J is the value of a field job, and then V, right? So V is the value of an unfilled job, vacancy. Okay. And here, so you will see this is the continuation value. Okay, so during every period you get W, and then for the rest, okay, for the rest of your life, then this is your expected value. Okay. So this forward-looking, right? So forward-looking behavior. So this is the power of dynamic programming, right? So you can kind of explicitly model forward-looking behavior. And then if you look at this, then you will get, try to interpret this equation. It's also very natural. And then for the firms, a few positions, right? So a few positions, so the flow return is how much the position can produce every period. So here in this model, there's a linear production technology. Okay, so a few positions, so a few job can produce Y units of output every period, and then you pay W, right? So this is the profit every period, and then the firm is subject to the same separation probability, right? So we will have similar interpretation as in the workers' case. So you can see the two things are sort of very similar in interpretation. Right? So this is the idea of the DMP model. Treat the workers and the firm symmetrically, right? As far as possible. And now you may be wondering, in those Bellman equations that you have learned before, sometimes there's an expectation, sometimes there's integral. So for example, in the macro model, on the right-hand side, there's a expectation things, right? So here, because in this simple version of the DMP model, we actually don't have uncertainty. There's no randomness there in the future. But you could imagine if you have a more general version of the model, you will have expected W, expected U, and everything expected on the right-hand side. But here you just say that there's no uncertainty. Okay. And then you have the benefit of unemployment, and then the benefit of a vacancy, right? Unfilled job or unfilled vacancy, and then you can easily interpret it. And for the worker being unemployed, you receive unemployment benefit every period, right? Small b. And then this is the probability of finding a job. This is a job finding rate. Okay. 1 minus m of this is the probability of not finding a job, right? So if you find a job, the benefit will be the value of working, right? W. And then if you don't find a job, the same U as before. And similarly for the firm, okay? So for the firm, a unfilled positions, unfilled job, the firm will have to pay a cost. Okay, so this minus K is the flow cost of keep a unfilled positions. Okay, so you can interpret this as like advertising cost, right? So you want to keep these unfilled positions. You are waiting for worker or searching for workers. Maybe you can imagine you need to run an ad in the newspaper. Okay, so therefore this is a cost minus K. And then this is the job filling or the vacancy filling rate, right? So the probability of find a worker. Okay, if you find a worker, the value will be J, the value of a job that we showed before. And then 1 minus this is probability of not finding a worker. Then the same value as this V, unfilled positions. Okay. So I summarize these things in my notes. So so basically I try to give you a map to understand the Williamson chapter, because it can be quite messy. Because if you look at Williamson's chapter, you have so many equations and you can easily get lost. So here I try to give you a map. So keep this in mind. So basically, even though you see many equations in Williamson, okay, try to understand that the model is actually summarized by these 6 equations. Okay, 6 equations, and then 6 endogenous variables that the model will have to determine. Okay, so here we'll look at these things, and then one useful way you can sort of organize this thing is that you first consider the worker. Okay, the worker. So the the worker will have a pair of equations. The value of work and the value of unemployment, okay? W and U. So to help us remember, I use this shorthand notation, Bellman W for work, right? Bellman equation of work. Bellman equation of unemployment. And then the firm will have these two equations, okay? Analogous to the worker, right? The Bellman equation for jobs, right? The Bellman equation for vacancy, okay? So worker has this, firm has this, and then Nash bargaining. The last one is the Nash bargaining. And so you have 1, 2, 3, 4, 5. And then the sixth is this so-called free entry condition. So the firm will keep posting vacancies until the value of vacancies equal to 0. Now, it turns out that now this, according to Professor Pisaridis, who is one of the inventor of this kind of model, it took him 10 years to figure out this FE. It's hard to believe. So he started to work on this sort of model when he was a PhD student in the early 70s. Okay? And then they keep working on this search and matching and so on and so forth. And then, but he, so he spent a lot of time, but it turns out that just the model is missing something. He has a hard time to do it. Okay, so not until in the early 80s, somehow he figured out that why not have these conditions? So it's hard to believe just because of this very simple thing. I said V equal to 0, then you get Nobel Prize. Right? Hard to believe. But this is according to Professor Pisaridis. He gave a talk at the Chinese University a couple of, maybe 2 years ago or 3 years ago. He talked about his history of this model. Now, why is it 0? Maybe you put it this way. So why is it 0? V equals 0. So basically because in the model, you see this K, okay, see this K is the cost of keeping a vacancy, okay? So you need to pay K every period in order to keep a vacancy open, okay? But then you have the option of not posting a vacancy, okay? So what is the cost of not posting a vacancy? So in the model, it is 0. There's no penalty for not doing it, okay? So actually this is the 0 is the benefit or the cost of not posting anything, okay? So therefore, if the V is positive, okay, because there's no penalty or nothing if you don't do it, okay? So, but as long as you do it, if the V is positive, then it means that it pays to do it, okay? So then if you assume everybody can post vacancy, okay? If you assume there are many firms in the economy, everybody can post a vacancy, then this is a very natural condition. So basically, so that's why it is known as a free entry condition. Okay, free entry condition. Okay, so as long as the V is positive, then firms will find it beneficial to post vacancies, and then when there are more vacancies, this job vacancy filling rate, okay, will go down, and then this will drive down the V. So it will drive the V down to 0, okay? And then this, then nobody will have more incentive to post vacancy. So that this V equal to 0 is the free entry condition. Analogous to so I guess the idea must have come from the idea of comparative equilibrium. So people repeat the Econ 101, right? Remember your principles of economics. So as long as there's a positive profit in a perfectly competitive market, firms will enter, right? New firms will enter, and they will sort of drive down the price until the profit is 0. And then no new firm will have the incentive to enter the market, right? The same idea. So again, Econ 101 is very useful, right? You get Nobel Prize by remember what you learned in Econ 101, right? Like Professor Pisaridis. So you have one pair of Bellman equation for worker, one pair of Bellman equation for the firm, and then the free entry conditions, and then Nash bargaining, right? Okay. So all together 6, and then naturally, why 6 equation? Because there must be 6 endogenous variables. So this 6 equation will try to determine 6 variables. And the rest of those symbols, they are parameters, right? So this small w taken to be a parameter. No, the discount factor, right? So, or the interest rate, the R, job separation rate, they are the parameter. Exogenous given unemployment benefit, they're the parameter. Okay. And whatever parameter in the matching function, right, such as the matching efficiency. Okay. And then the approach in the in the book is that Williamson tried to manipulate these 6 equations. Okay, try to combine them in a certain way, right? So if you are patient enough, you can go through the algebra. But he made a lot of mistakes, okay? I can tell you. There's quite a lot of things, plus or minus or whatever, okay? But I guess it doesn't really matter. What matters is that try to understand why he want to do it that way. So maybe first, imagine, suppose if you don't care about analytical solution, suppose you can somehow you only care about numerical solution. You don't need to do those algebra, right? Because if you have a computer, if all you care is find out the numbers for the W, U, J, V, W, Q, if you know the value of the R, delta, and so on and so forth, presumably you can solve these 6 nonlinear equations, right? Okay. So you can actually solve it. Now, it's almost like linear, but it's not quite because your theta is here, right? So your theta is inside this function. Let's say, suppose you take this m to be the conductor's potential function, and then you have this multiplication v and so on. So it's slightly non-linear, but still you can imagine if you fix all the parameter value, you have 6 nonlinear algebraic equations. You may not be able to solve it by pencil and paper, but your computer should be able to do it, right? So in principle, there's no problem in solving this system numerically. But just the property of the solution, you don't know, right? Because numerically, you may not be able to find out whether there's a unique solution or maybe there's no solution or multiple solution, right? So that's why an analytical solution is still useful, right? Because the analytical solution will kind of tell you the properties of the model, right? Okay. So the Williamson approach is that he look at this sum. Okay, so this W minus U plus J minus V, this is the total surplus. W minus U is the surplus of the worker. J minus V is the surplus of the firm. The sum of the two is known as the total surplus, and then he replace it by S, capital S. Okay, so sort of like changing some of the variable and then do algebraic manipulations. So you end up with two equations. So after quite a lot of work, you end up with these two equations. Okay, so basically by algebraic manipulation, you have 6 equations in 6 unknown, and then you do algebraic manipulation, you combine the 6 equations into 2 equations in 2 unknown. But now the unknown is S and theta, where S is known as the total surplus, the sum of W minus U and J minus V. And then you plot out these two functions, and you have the picture. You have this nice picture. Okay, now from the nice picture, you'll see that there's only one intersection point. So then you end up with this. This will be the equilibrium total surplus S star and the equilibrium theta star, equilibrium tightness. And then given this, then you back out, you try to recover all other endogenous variable using your previous equation. So this picture shows you the solution is unique, right? So the 6 equation system should have a unique solution, which is clear from this picture, whereas if you use computer, it's not really clear. You don't know, right? Okay. And this picture will also quite useful in doing comparative statics, right? Like what we did last semester, right? So we also use picture to do comparative statics, like what's going to happen to the equilibrium if the unemployment benefit go up, what will happen if some other parameter change and so on, right? So you can look up, so for example here, from the picture, you can easily draw the conclusion about what about there's higher productivity, right? So productivity is the Y. So you look at this curve, you look at this curve. Now this curve has nothing to do with Y, right? So this curve won't change. And then if you look at this curve, you look at this curve and you see the Y here, right? So you see the Y here. So when Y goes up, all other things constant, you kind of shift up this curve, right? So you can also see this vertical intercept, you only got the Y here, right? So you keep other parameter constant, you only make a Y higher, so this thing should be higher. Right? So you end up with a upward shift of this downward sloping curve, and then the new intersection must be higher tightness, right? Higher tightness, and also a higher total surplus. Okay, and then you can use other equation to find out once you have higher tightness, what will happen to the wage and so on and so forth. Okay, so there. So this picture can be useful too, right? So this is one way to do it, and in the lecture notes I show you another way, which is a more popular approach, and I think it also might help you understand the model a little bit better. Okay, so I show you step by step. Okay, so I break up the whole things into 7 steps, 8 steps, and so on. But the idea is the same, because if you look at this 6 equation system, 6 unknown, it's very hard to know the property of the solution. So the objective is to reduce the size of the system, right? So you have 6 equations and 6 unknowns, so you want to substitute out, basically make it reduce to 1 equation and 1 unknown, or 2 equations and 2 unknown, right? Okay, so this is the goal. So here, this is the original system. So you have these Bellman equations, okay? And then we also show you last semester, this kind of Bellman equation is known as the Bellman equation in stock form, right? In stock form, because this W, U, J, and V, these are the value in present value, right? So the benefit in present value, the lifetime utility or the lifetime profit, right? So the summation, basically just like the objective function, right? Summation from t from 0 to infinity, and then you discount each period by beta to the power t and so on, right? So these are present value. This is what we call stock present value. Just like you have, you expect you have an income of 1 million every year, and they say you will work for the next 40 years. And how much money do you have in present value? You can calculate, right? This sum, so you sum up all this 1 million, 1 million, 1 million, many years, but then you discount by the discount rate, right? So these are the stock. But then, given the fact that you have that much of money, 40 years later, you can also calculate the equivalent flow every year. Right, so this is the annuity problem. Just like when you retire, if you receive a sum of money, you can give this money to a bank, and then you want to buy a pension fund, right? Annuity fund, and then you have a formula to calculate this, let's say $1 million worth how much money every year for the next 40 years, right? This is called annuity, right? Okay. So the annuity concept is the flow value. So the flow value is step number 2. So step number 2 is just try to convert, just try to write these stock things into flow. So all you need to do is just multiply 1 plus R on both sides, collecting terms. That's the only thing you do. Okay. So so basically, step number 2 is just a rewriting of the Stock-Bellman equation into flow-Bellman equation. So there's no reduction of the system yet. So if you count the number of equations, it is still 6. Okay, just rewriting. But this is useful because this kind of Bellman equation is actually well known in finance. Okay, so this is called capital equations. Okay, so the flow value of a asset. Okay, so the flow value is that every period you receive that much of income, and then this is the capital gain term. Okay, so this kind of thing is used frequently in continuous time. So in continuous time model, there's another term is the W dot. Okay, so the over time this value can change. So here it has a very nice pattern. Okay, so the nice pattern is that the left hand side is the annuity value. Okay, so the annualized value of this assets. So the interest rate times the stock. Okay, so this is a flow value. So every time you have this flow, and then this is the alternative. Okay, so if you change the state from W to U, so this is the U minus your original value multiplied by the probability of the change. Similarly, if you look at this second equation, you have similar interpretation. So here, this is the flow value of being unemployed. So here you receive benefit of B, and then there's a probability. So this one is the probability of changing from unemployed to employed. And then the improvement in the value is W minus U. Okay? Now, similarly, you look at this BJ and BB, similar interpretation. Left-hand side is the flow value of a job, of a few jobs, and then every period you receive that much. The output minus the wage you pay out, and then there's a probability, right? So the job separation probability is the probability that you change from J to B, right? And then the improvement is V minus J. So this is a nice formula, right? So sort of follow the same pattern. Same pattern. And then when you look at the solution of the Nash bargaining problem, okay, so the Nash bargaining problem is that you try to maximize these things, right? So you try to maximize these things, and then the first order conditions, you can see that the first order conditions looks like this. And the simple way to get this first order condition is that because you have these restrictions, this surplus has to be positive, and you have this power over here, so you can take log, right? So you can take log would be you take log first, and then you differentiate. This will be the easy way to get the first order conditions. So you get the first order condition that looks like this. You take log and then differentiate. Now, yeah, there's a typo here. This should be alpha, right? Obviously, not beta, but alpha. So, so we need to change all this beta to alpha. But anyway, the result is a well-known result. So the solution of the generalized Nash bargaining is that the worker and the firm will each receive a fraction of the total surplus. Okay, with the size of the share determined by the so-called bargaining power parameter. Okay, so it sort of looks like this. Okay, so this is the well-known result, Nash bargaining solution. So the workers' surplus, okay, so will be a fraction of the total surplus. Okay. And obviously, you can also, by moving this W minus U to the left-hand side, you get another way to write down the same results, right? So you can kind of write it this way. This might be more convenient for algebraic manipulation, right? But just the same kind of result, right? Just algebraic manipulation. So, but this one is perhaps easier to memorize, right? So the result of a Nash bargaining is that the firm and the workers each will receive a fraction of the total surplus, right? So this share the total surplus, and then the size of the share will depend on this parameter alpha between 0 and 1 that represent the bargaining power of the party. So step number 2 is just a rewriting, right? Just for rewriting development equations. And then step number 3, still not yet reduce the system, still try to rewrite something. Okay, try to rewrite something. So the way is that try to solve out W minus U and then J minus V. So the way you kind of do it, for example, so let's say you look at the in step 2. Suppose you look at the first equations. So just by algebraic manipulation. Okay, so this one you can just let's see here. Yeah, so just algebraic manipulations. So this is capital W. Okay, so just do that, and then you see this W things on both sides, right? And then you can sort of move one of them to the left-hand side. Okay, so you get this. Okay, and then you can see. You can divide you get this, right? Okay, and then you can minus U on both sides. Right? Minus U on both sides, and then do it that way, and then you and then you will have one delta U, you cancel out one of them, right? So you will get something like a minus, right? So you have yeah, with a plus here, then minus out U here, and then you put them together. Okay? So this is how you get it, right? So just simple algebraic manipulation. So algebraic manipulation. So basically, you by algebraic manipulation of the first equation, so you kind of write it this way. Okay, in step 3, similar algebraic manipulation by the BJ equation. So you end up with this step 3, and then the rest you keep it the same. And as I said, the Nash bargaining equation, again, you want to, because you see this W minus U on the left-hand side, W minus U on the right-hand side, you collect them together, right? So you end up with this. Now, the reason why I want to do it this way is because you got this W minus U here, and then you got W minus U here, and then you have W minus U here. J minus B, J minus B, J minus B. So you can kind of change the variable into this. So you have W minus U and then J minus B. So still you have 6 equations. But then you kind of change the variable. Rather than looking at W, you look at W minus U. Rather than looking at J, you look at J minus B. And there's strong reason why you want to do that this way, because you can substitute out this W minus U thing, J minus V, and so on. Try to substitute out. Okay. You see, if you don't do it that way, it's quite hard. Suppose you go back to step 2. If you don't do it that way, you have W appear everywhere. You have U appear in many places. The only easy thing you can do is to substitute out the V, right? V set to 0. You set it to 0, 0, 0. But this is very hard. Okay, it's very hard to manipulate. Because remember that the goal is to reduce the system into 2 equations so that you can draw a picture, right? Okay. So there's a trick. There's a little trick like that. So the trick is to do it like this. Okay. So once you have this, then you can start to reduce the system by substitute out W minus U, J minus V, and so on. Okay. And by setting V equal to 0. Okay. So you substitute out 3 variables. So at step 4, I only substitute out 2 variables, the W minus U and the J minus V. Okay. So you substitute out 2 variables, then it means that you will reduce the number of equations from 6 to 4, right? So you have something like this. Just straightforward substitution. Now, once you have this, then you'll see there will be pretty easy to go for another step of substitutions. Okay. So because your J is here, so you already have a solution for J. Okay. And then J only appears here, so it's very easy to substitute out. Basically, very easy. And this is what we try to do. Substitute out the J. So you substitute out the J, you end up like this. Okay. So you have 3 equations, 3 unknown. Okay. And you already see something. So this is known as the job creation conditions. Okay. So this one actually has a very nice interpretations. Okay. So this one is kind of capture the demand side of the labor market. Okay. Demand side of the labor market. So here is that you have Y minus W. So every period, a few jobs will give that much of profit to the firm, right? So Y minus W is the every period, a few jobs